My name is David Colson. This is MEC 116 is the final lab. We are powering a singular LED using a 208 voltage plug. So in order to make this work, we have used 27 Henrys worth of inductance to bring our current down to 20.4 milliamps, which should be just right for our LED. We're using a full bridge rectifier to turn that AC signal into a DC signal. And with that, we should be able to throw the switch, which normally powers that gigantic motor down there, to power just this LED. This may result in an explosion. Let's find out. Yep, we blew something. We blew that. I saw that flash right there. Yep. So we blew the diode. Okay, take two. I believe I messed up the bridge rectifier, so we're gonna try this again. And there it is. Our circuit is complete and it works. Okay, now let's talk about why this works. So in an AC circuit, when it comes in off the wall, voltage and current are perfectly in phase, ideally. That means that when current and voltage both peak, we get 100% of the power available at that peak. And then they come down to reverse and we get the current and voltage peaking at the bottom. So this is P is equal to V times I. So when it's out of phase, we'll see that when we have voltage peaking there, current is at 0. So when we multiply those across, we have 0. Or here in the middle, voltage is peaked low, but current is again at 0. So when we multiply those across, when we multiply them across, we get 0 again. So this limits the amount of power we have in the circuit by making this multiplication across the two out of phase lower. So, in a circuit, what happens when we add inductance is it acts like a resistor. And we call that resistance created by inductance impedance. Well, impedance is the sum of all resistance in the circuit. So, in order to figure out exactly how much impedance we need in the circuit, we are going to determine how much our LED needs optimally. Now, we know it's 3 volts. We know it's a maximum 20 milliamps. So we can just do some math to figure out exactly what it should ideally be at in resistance at that point. Now, LEDs are semiconductors, so that means that their resistance changes depending on the current run through them. So it should be about 150 when we have 3 volts and 20 milliamps. So from there, we can calculate the rest of the calculations we need in order to arrive at the number of Henrys we need in order to get right to that amount of current. So what that looks like in our math, the results come out to this. So once we figure out the resistance of the LED, the voltage should be in the amps, then we can go back using our known source voltage, do reverse calculations to figure out what the impedance should be. And once we know the impedance, we can determine the reactance of the inductor. And from there, once we know the reactance, we can determine the Henrys. And then once we have the reactance, we can also calculate the number of volts it will drop. So that's how we calculate out this whole thing. Of course, I don't have a 0.6 Henry inductor, so I have to use either 27 or 30. I did the calculation for 30 here. Additionally, in order to use fewer Henrys, let's say I have fewer materials, I could do a half bridge, and that would bring me out to 15 to 13 Henrys, giving me that for the full wave, and then I would cut that in half with a half wave. So this is the math for all the solutions I have for this lab. So when we use impedance this way in a circuit, it acts essentially as like a resistor, and we're tuning that resistor size to drop just enough voltage that we've got the perfect amount left over for our LED. Now, the problem with this is it's super inefficient. So all of that power is basically being tapped back to ground, and we're losing it. So the circuit's still consuming all of that power. So the apparent power that is being pulled from the circuit, or the true power that's being pulled from the wall is still 208 volts and so many milliamps. but we're only using 3 volt for the LED. So if we wanted to avoid this and have a more efficient circuit without wasting all of that power, we would use transformers. So transformers step down the voltage very efficiently, allowing us to run the LED without wasting all of that excess power. One more thing, the lab actually asks me to power 2 LEDs, so there they are. And that wraps up MEC 116 AC circuits.